Okay, everybody. So in the last one, we did a quick review of functions, and I emphasize quick. These are meant for people who have seen functions before. So I want to talk about a few details. There's going to be a few more videos digging into some of the details, and we'll go through a bunch of kinds of functions. And in this particular video, I want to talk about the domain and the range of a function. Okay, these are additional pieces of our function that we should talk about. So let's just quickly remind ourselves that one way we can think about a function, right, is we take something, I'll use x to represent that something, and we put it into something, a little machine that's going to represent our function, and that function does something to x and spits out a new value, right? So we talked a little bit last time, functions don't necessarily have to be about numbers, but let's focus on that because that's what we'll be focusing on in this and the following videos for a while. And so we input some value, some number into our little function f, and f does something to it and it spits out what we call f of x, the value associated to that. So we often call x the input, f of x is the output. And here's where domain and range come in. We will call, or what we call the domain is going to be the collection of all allowable inputs, right? And our range, I guess we could call them the achievable, oops, I don't know what happened there. The achievable outputs, right? Meaning given the things we're allowed to put into it, what are the things that will come out of it, right? So not every function can take any old input, and not every function can get you to every output among all the numbers, okay? So when we talk about domain and range, there's two big ways we're going to talk about it. The probably easier one is when our domain is determined. Oops, domain is determined by, let's say, the real world. Let's just say the application, right? It might not necessarily, it might just be determined by, I'll just say by the application, what it is we're trying to do with it. So here, let's do a quick example of this. Let's say I have a function. Let's say I travel from home and I walk away from my home at a constant pace of 2 meters per second, right? I could come up with a function, d of t, which gives us the distance from home in meters after t seconds, right? And this function would just look like 2t, right? After the first second, I'm 2 meters away. After the 10th second, I should be 20 meters away. So what's the domain of this function? Well, because of the nature of this problem, right, it doesn't make sense to talk about negative numbers, for instance. There's the moment I start, presumably at home, so 0 seconds, and then every second I walk after that, right? So we might say that our domain, let's say I can just write it this way: t is greater than or equal to 0. Actually, let's be more careful. We know I'm not walking forever, so we'll say that t is going to be between 0 and, I'll put capital T, some number that when I stop, maybe it's 30 seconds, whatever. It should be given in the problem if it's important to the problem, right? So here, there's nothing about this function itself, the mathematics of it, right? I can take 2 and multiply it by any number, but because of the nature of the problem, this function doesn't really make sense, right? I'm not negative meters away from my home when t is equal to -5, right? I'm starting my clock when I'm at my home, walking 2 meters per second away, so it only starts at 0 and grows larger, okay? So in this case, this domain is determined by the nature of the problem, right? Another way to write this would be using interval notation between 0 and that capital T, whatever that number is, okay? So whenever we do applied problems where there's some kind of maybe real world application, or just I might just decide, or someone might decide, we just want to consider things for certain values, those are either going to be implied or given in the problem. So it's usually a bit easier to come up with the domain, right? And consequently, maybe consequently, sometimes it will also make the range fairly obvious, right? So what does that mean for the range? Well, it's pretty easy to determine in this case, right? When t is at a minimum, d of t, right? The minimum d of t can be is 0, and then after capital T seconds will be 2 times capital T meters away. Okay, that one's a pretty straightforward to determine. We will typically be more interested in determining the domain, though there are instances where we want to determine most. Let's talk about maybe the more difficult version of this, when the domain is determined by, I'm going to write the math. Okay, so what I mean by this is something about the function itself mathematically might determine what numbers this function can actually act on. Okay, so let's give a classic example. Let's say f of x is equal to 1 over x. Okay, so assuming there's no application here, there's nothing in the real world that tells us anything about what x's can be. If I ask what's the domain, the convention is, what I'm really asking is, what are all the possible numbers that this function can work with? So in other words, what numbers mathematically do we know how to take 1 and divide it by that number, or what numbers have a reciprocal, right? Well, you can do this to any number except for 1. We can start at -infinity and go all the way up to 0, but we cannot include 0, right? 0 is our single value that cannot be cannot be divided by, right? Doesn't have a reciprocal. But then there's also all the positive numbers. So we have our little union symbol, and we can go from 0 up to positive infinity. We might also write this as, let's say x is less than 0, or x is greater than 0. Both of these are a bit cumbersome, and so often when we have ourselves in a situation where it's easier to say what isn't allowed, convention would have us say something like, you could write this domain, we could say the domain is all x except x equals 0. We might even go even farther and just write x is not equal to 0. And this is understood to mean everything else, right? And so we don't have to write these kind of cumbersome notations or sentences. We can just write something like this. When there's only 1, maybe 2 or 3 values, then we might choose to write it in this way. None of these are wrong, but it's typical to use this last one. Okay, sometimes it can be a little bit more complicated than this. Let's do one more. G of x. We'll do more than one more. 1 over 1 minus x squared. Okay, so we might notice last time the problem was division by 0, and that's still the problem that we have here. We can't divide by 0, right? In other words, I need to make sure we don't have a problem with x being 0, right? So this is a common misunderstanding. We see division and we think we don't want to divide by 0, so let's make sure x is not 0. But in this case, x being 0 doesn't make us divide by 0. So what we need to make sure that 1 minus x squared is not equal to 0. We could solve this. There's a few ways. I'm going to choose to factor it. So this can be factored into 1 minus x, 1 plus x should not be equal to 0, right? So what would make this equal to 0 is if either one of these factors is 0. So in order for this statement to be true, we need to make sure that 1 minus x is not equal to 0 and 1 plus x is not equal to 0. In other words, x is not equal to 1 and x is not equal to -1. So if we were to ask what's the domain for this, we could write, we'll do very shorthand, x is not equal to plus or -1, right? We mean it's not either equal to either of those, right? A more convoluted way to write this might be something like -infinity to -1, -1 to 1, union with 1 to infinity, right? So we're getting all the numbers except skipping over those two places where we have an issue. Okay, let's do one more. Actually, let's not do one more, or we will do one more with domain, but let's do something first. So when we're talking about domain, there are a few things we need to consider. Let's say mathematical restrictions. This is not going to be a comprehensive list, but this is going to be a pretty comprehensive for us, okay? So these are the things we have to look out for or consider. We need to make sure there's no division by 0. We need no negatives with even roots, right? We can't take square roots or fourth roots or sixth roots or eighth roots and on of negative numbers. We're not using complex numbers in these videos, so we won't be taking roots of negative numbers. So we don't allow negative numbers into our even root functions. Inverse trig have very particular domains, right? And I'm not going to go through those right now. It's a whole big conversation. But remember from your trig class, trig functions don't really have inverses unless we restrict their domains by restricting restrict the domains of the trig functions when we have their inverses, which really gives us a restricted range of our inverse trigs. But the trig functions, inverse trig functions domains are restricted by the range of the trig functions themselves, right? Between -1 and 1, if we're talking about sine and cosine, so on and so forth. Sorry, that was a mouthful for me there for some reason. In any event, these are a good place when we have inverse trigs to consider what we are allowed to put into them. Log functions. I'll say it this way, no let's just say log functions need inputs greater than 0, right? So no zeros, no negatives for log functions. Those are the big ones that we'll be looking for. So anytime you see some kind of division, like a fraction, look for zeros in the denominator. Roots, be careful about negatives. Logs, be careful about negatives and 0. And then inverse trigs, depending on what they all have their own conditions, right? So mathematically, those are the big ones. If there's nothing from the application of the problem, then this is what we consider. So let's do one more example with domains. Let's look at this function. F of x is equal to, let's combine a couple of these. Let's say we have the natural log of the square root of x minus 1. Okay, so here we see we've got a couple of these things going on. So we know we need two things to be true. I notice that I have an even root, right? That radical without anything by convention is taken to be the square root, the 2 there. And so I know that I need x minus 1 to be greater than or equal to 0, right? Because if I don't have this, the square root can't deal with it. So that's our first condition, and we can rewrite this as x being greater than or equal to 1. So this is not the answer. I'm circling it for myself so that I don't forget this piece of information. Whatever my answer is, this has to be true. X is greater than or equal to 1. We also need that this square root itself is greater than 0. Right? Because otherwise natural log won't know what to do with it. Well, this part's simple because first of all, we know that this is going to be positive because it's the positive square root, right? This only spits out positive or 0 numbers. So with that in mind, we have to think to ourselves, well, let's just make sure this is not 0. In other words, let's make sure x minus 1 is greater than 0. As long as it's positive, as long as x minus 1 is positive, its square root will also be positive, right? Which means x has to be greater than 1, right? Can't be equal to 1 because if it's 1, the square root is 0. Natural log doesn't know what to do with 0, and f breaks down. So we've got two things that we need both of them to be true. I don't know why I circled that. It's pretty easy to see there's two things. So we need all the numbers that are greater than 1 and equal to 1 as one condition, and we also need the numbers that are strictly greater than 1. So for both of these to be true, we need x greater than 1, right? So if this isn't totally clear, any number that satisfies this also satisfies both of these, right? It's pretty obvious that it satisfies x greater than 1, that's it, right? Well, if we pick a number greater than 1, like say 2, is that greater than or equal to 1? It is. If we pick another number greater than 1, like a billion, it also satisfies x being greater than or equal to 1. If we try to include 1, that satisfies this condition on the left, but it breaks this condition on the right, and we need them to be true. And so the number 1 can't be included, and so our domain is strictly the numbers greater than 1. Okay. Okay. Let's talk for a minute about range. Range it can be a bit trickier. We don't have a nice set of rules necessarily to determine if what the range is going to be, like we do with the domain, where we have these restrictions that we have, right? One of the main ways we're going to determine domains, and we're going to learn some methods, you'll learn some methods in calculus that'll help us determine domains. But more importantly, at this point is just getting familiar with certain kinds of functions. So for example, if I have the function h of x equals 2x minus 1, and I want to know its domain, well, first of all, mathematically, are there any numbers that I can, so this function asks me to double a number and then subtract 1. And there is no number that I can't do that to, right? So this domain is all real numbers, right? So I can write it this way, I can write it this way. I can say all real numbers. I could say x between negative infinity, infinity, right? These are not all required. Any one of these 4 notations is perfectly fine for this. The range is all the possible outputs, right? And so if we think about the graph of this function, Just do a quick sketch. It's got a y-intercept at -1. Let's put that there. It's got a slope of 2. Something like, I missed the dot, but that's all right. Let's move that to go through the dot. So there's our graph of this function. I've drawn those little arrows. We're all familiar with lines. It just keeps going on and on and on, right? It will eventually reach every single value in the y direction, right? So we can put in any value of x, and it will eventually spit out any value of y that we want, right? If I picked a value of y up here, I just need to look somewhere out on the line as it continues on to find the point that has that y coordinate, meaning it has output that value. And so this has the same range, right? This is not always the case that functions have the same domain and range, but in this case, it does. I can prove it algebraically, right? When I claim that the range is R, what I'm claiming is if you throw me any number, I can find an input that takes me to that output, right? So we can see that quickly. If somebody challenged me and gave me some number, I'll call it K, and said, prove to me that this function has an output of the number K, whatever that is. Well, I can see that if I do a little algebra here, if I take their number, add 1 to it, and divide by 2, that input will give me that out, right? So if somebody was, for instance, wondering if I could possibly get the output of 101, then I can tell them, well, if you input 101 plus 1 divided by 2, which is 102 divided by 2, which is 51, h of 51 will be 2 times 51 minus 1. There's my 102 minus 1, or 101, right? So I can do this for any number. You tell me what number you want this function to hit. I'm going to add 1 to that number, divide by 2, and now I can tell you how to get there, right? So this is one way to sort of prove to ourselves that this range is all real numbers. But we're not going to really go through that. When we see a line, unless it's a horizontal or vertical or a horizontal line, we know that the range is going to be all numbers, because if it's got any slope, whether it's positive or negative, it eventually goes through every single y value somewhere along that line. Let's do one more, something else we're familiar with. Let's look at a function k of x. Let's do x minus 1 squared plus 2, right? So here's another one with the domain of all real numbers, right? Why? Well, because first off, we go to our checklist for domains, none of those like warnings are up there, but it's also pretty clear. If I can take any number and subtract 1 from it, no matter what that gives me, I can square it, and no matter what that gives me, I can add 2 to it. So there's not a problem with any number being input into this function. But what about what comes out of it? This is a lot more complicated than the last one. I don't know the algebra I need to do to kind of figure out what this does, but I am familiar with the graph of this function. Right? And maybe you remember these, maybe you don't, maybe you need a little more review. This is a quadratic opening upward with a vertex at 1, 2. So it looks roughly like this. Okay. Well, again, just using the knowledge, so let's put this in, this is the point 1, 2. Using the knowledge I have of quadratics, of parabolas, I can look at this graph and see, well, what's going to happen? I can get any y value by simply moving further away from that vertex, right? The further up you want to go, I move further away from that vertex. So I can get all these values above 2 by moving further out. But there's nothing I can do to get below 2. So the range here, let's use interval notation. The range here is going to be outputs 2 and greater, right? Because there's no, you can see on this picture, there's nothing below that value there, right? So this is a lot of the time how we're going to do range. We're going to just have to use our knowledge of functions, right? So exponentials have a set of, have a known range, and then we'll have to think about shifting and stretching and all that kind of stuff. But the basic idea is taking that catalog of functions, which we'll go through some of them briefly in the next video to get the range. And as we go through them, we'll talk more detail about range of the big functions that we're going to be looking at it. Okay, that's it for this one. Domain and range. I will see you in the next one. Thanks, everybody.